A sequence an is called increasing if its terms are increasing as n increases. So if an is less than an plus 1 for all n bigger than or equal to 1, then the sequence is increasing. In other words, a1 is less than a2, which is less than a3, which is less than a4, etc., etc. And a sequence is called decreasing if its terms are decreasing. You could write that as an is bigger than an plus 1 for all n greater than or equal to 1, or you could also write it as a1 is bigger than a2, which is bigger than a3, etc., etc., etc. A sequence is called monotonic if it's either increasing or decreasing. We say it's bounded above if there's some number m for which all of the terms are less than or equal to m, for n bigger than 1, and it's bounded below if there's some number, lowercase m, which is less than or equal to the value of all of the terms of the sequence. So it's less than or equal to an for all n greater than or equal to 1. And a sequence that's bounded both above and below is called a bounded sequence. And here's another very useful theorem. Every bounded monotonic sequence is convergent. So if a sequence is bounded above and below, and it's either always increasing or decreasing, then it has to be convergent. How would we actually check to see if a sequence is monotone? Well, one way is if we could use our trick of replacing the n by an x to get a function of x, and if that function was differentiable and had a derivative which is either always positive or always negative for x bigger than 1, then that would tell us that our sequence was either increasing or decreasing for n greater than 1. There are also other ways, but of course they're going to depend on the formula for an. Well, here's an example where that trick actually does work. Suppose I want to show the following sequence is monotone, either always increasing or decreasing, and bounded. And if I know that, I know it converges according to the theorem. So let's look at the sequence whose nth term is tan inverse of n, and n runs from 1 to infinity. And I know minus pi over 2 was always less than or equal to tan inverse of any number, which is less than pi over 2. So this is certainly a bounded sequence. And now I can replace the n by an x here and get a function of x. And it turns out that that function has a derivative. And its derivative is 1 over x squared plus 1. And this derivative is positive for all x. Therefore, this is an increasing sequence, and it's bounded, so therefore it satisfies the conditions for the monotone bounded sequences in the theorem. We can conclude that it converges. Now, in fact, we can actually compute the limit here, but the theorem itself just tells you that it converges without directly computing the limit.